All right, this is the kinematic units notes. This will be divided up into 3 videos, so let's go ahead and get started. The learning goals for this unit: you need to be able to use motion graphs to explain what an object's doing. You need to be able to solve kinematics problems, and with the AP, that usually means 2 unknowns. And you need to be able to solve problems involving projectile motion. All right, so kinematics. Basically, this is the study of motion. Now, motion can be divided up into 2 categories. First, we have translational. That is linear, or along a path. The second type is rotational. And that's around an axis. Think about something spinning for rotational. This unit we're going to solely focus on translational, and the next unit will focus on rotational. All right, so when it comes to motion, we have 2 types that we want to start our study with: constant velocity and constant acceleration. You will get constant velocity when all of the forces acting on an object are balanced. And you will get constant acceleration when the forces acting on an object are unbalanced. And in the previous unit, we talked about how for unbalanced forces, we had Newton's second law, which stated that net force equals mass times acceleration. So right after that, we got an acceleration that we can use for kinematics, studying motion. Motion itself can be described using graphs, formulas, and we can use those graphs and formulas as models to describe. We get the formulas derived from graphs that help us to understand what's going on with motion. Now, for constant velocity, again, this is when the net force equals 0. This is an even change in an object's position over time. Now, position is an object's location at a given time. And I think football fields are going to be a great example for this. So, for example, the ball may start on this 10-yard line, and it may travel to, let's say, the 50-yard line. So this first part would be x naught, and this final one will be x. The displacement, which is a vector, would be the final position minus the initial position. So in our football example, the displacement then would be 50 minus 10, which would be 40 yards. So the displacement would be 40 yards. And if I were to say that this were the positive direction, backwards would be negative. I could then say we have a positive 40-yard displacement. Imagine, though, that the ball went from here to here, but then came back to right here. So this is now x. Well, now our displacement would be 30 minus 10. So it would be 20 yards. And notice it would still be positive, even though the ball went in the negative direction for a certain point. Now, the total distance the ball travels, it would be 40 plus 20, it'd be 60. So the ball travels a distance of 60 yards, but its displacement would only be 20 yards. So you have to be very, very careful with displacement. Let's say an object is moving at a constant 5 meters per second, starting at 0 meters. Well, that means in that 0 meters, the time would be at 0 seconds. At 1 second, it would have gone 5 meters. 2 seconds, 10 meters, 3 seconds, 15 meters. I think you'll probably get this pattern pretty quickly. But this is what it means to travel at a constant velocity. The displacement is even for each second. Notice how each second gets 5 meters worth of displacement or position. the object's position changes 5 meters for every second, no matter where you look. If we were to make a graph of this, where we can put time on the x-axis, this is a 20 by 20 grid. So on the x-axis we have time, measured in the second. On the y-axis we have position, measured with a meter. We can go ahead and plot this data. Hopefully you notice that this gives us a linear relationship. So we can draw a line of best fit. Oh, I didn't like that. See if I can draw a better line of best fit. I'm freehanding this, but you should use a ruler. Whenever you look at a graph, there are two things you have to understand: the graph's slope and the graph's area. Always understand what the slope represents and what the area represents. So first off, for slope, if I wish to calculate the slope, I would choose 2 points on this line. I'm going to choose those 2 points because they're convenient. So here I have a position of 17 meters, a position of 3 meters. Here I have a time of 3.5 seconds, and here I have a time of 0.5 seconds. So the slope would equal 17 meters minus 3 meters divided by 3.5 seconds minus 0.5 seconds. And if I get a calculator and work that out, 14 divided by 3. I get 4.6 meters per second. Pretty darn close to 5 meters per second. And the reason why it's off is because I freehanded it. So what we see here then is that the slope gives us the velocity. So the velocity equals a final position minus the initial position, final time minus initial time. So in other words, velocity is delta x over delta t. Area. If I looked at the area under this line, it'd be like a triangle, so 1/2 base times height. The units would give me a meter times a second. I'm not sure what that is. So in this case, I would say the area has no meaning. And that's okay. It's okay if something has no meaning, but you do need to recognize that it has no meaning. Now, since this line is a straight diagonal with a slope, we can say it has a constant velocity. So if I were to take a look at a velocity versus time graph, well, this would be a horizontal line at 5 meters per second. And if I were to take a look at an acceleration versus time graph, well, if something has a constant velocity, it means the velocity is not changing. Acceleration is defined as a changing velocity. So if it's not changing, it has 0. meters per second per second. So that's what constant velocity would look like on the velocity and acceleration graphs. Okay, well, what if the position graph looks a little more complicated? Well, in this case, we need to take a look at the slope of the tangent line. So looking at this line, we can choose several points where we could try to find the slope of a tangent line. And notice that what we have here is we have an object that has positive velocity to 0 velocity to negative velocity back to 0 velocity. So the velocity is changing here. So obviously the whatever the object did to make this graph, it is accelerating. And what we want to do is we want to take a look at the velocity at a single moment in time instead of the entire trip, because it's changing. I want to know what the velocity is at a single moment. We call this instantaneous velocity, and we calculate it using a limit. So the instantaneous velocity would equal the limit as time approaches some value on the graph of delta x over delta t. It's up to your math instructor to teach you about limits. And here we're starting to get a little off course, but this does lead us into calculus. What happens is that the delta signs become d's for derivatives. So we'd want to use the derivative. So for those of you in calculus, let's take a look at a quick example here. Let's say x equals 2 plus 3t cubed is an equation which describes the motion of an object. What is its instantaneous velocity at 2 seconds? Okay, well, first off, we want to write down our equation. Then we want to take the derivative with respect to time. So that would equal 0 plus 9t squared. So that means that the velocity equals 9t squared. So if we plugged in 2 seconds into t, the velocity would equal 9 times 2 squared, or 36 meters per second. So the object would be traveling at 36 meters per second at 2 seconds. All right, that concludes video 1.